Не проверите, работаем. Ну, как бы работает запись. Ага, если не сложно. Yeah, so the next step. The next step is to discuss the following important problem.
У вас должна быть новая трансляция.
Да. Все пошло? Ладно. So the next step is yeah. So I had a question on the during the break. So please let me just this is lemma. So if yeah, so this is what I have written, that dimension of orbit is equal plus the dimension of stabilizer is just equal to dimension of the group. So this follows from the following. Just apply. So in order to establish this, you recall that we start from action of G on X, and you have an orbit morphism that maps a point G of your orbit to the point Gx on X. Yeah, so we fix a point on your variety, and so this maps the group to our orbit. And this is, of course, surjective. And we can write down that on the open subset, the dimension of fibers, so just if you take Z, here the dimension of the preimage of Z is equal to dimension of G minus dimension of Gx. But notice that all fibers, so fibers here, are isomorphic to the corresponding cosets of stabilizer. So if you take Gx, so the fiber over is just the stabilizer of the conjugate of the stabilizer of G, yeah? So or so it is stabilizer of Gx, and this yeah. So actually no. So the fiber is a coset. Yeah. So the fiber over X itself over X is a coset, is the stabilizer of G. The fiber over Gx it is the set of elements that just yeah. So the fiber over Gx, it is the set of elements that maps Gx into Gx. Yeah. Yeah, so yeah, I'm talking about two different fibers. So just these are elements. Yeah, so these are elements H. Yeah.
Excuse me, can you say write down a general statement which you use for calculating dimension?
Dimension of the fiber. Yes. So let me write it down. Just. If you have X in Y, the morphism between algebraic varieties, then here you have open subset such that if you take point from this open subset, the preimage of, so if this map is dominant, and actually the map is surjective in our situation, then preimage of Z is dimension of X minus dimension of Y.
It's just for a point of an open subset.
Yes. Yeah. But here we want to say that the points over, I want to say that what is the fiber? Yeah, so the fiber over, so I take the element Gx, yeah? So I have to consider the elements H, yeah, so such that I apply H, so the fiber over Gx, so it is preimage of Gx. It is elements of H such that I apply H to X and get Gx. Yeah? So this is saying that the element G inverse X, G inverse H fixes X. Yeah? G inverse X, G inverse H, X is equal to X. Yeah? So this means that G inverse X is in the stabilizer, meaning that H belongs to the corresponding coset of the stabilizer, like this. Yeah? And notice that dimension of Gx and so dimension of Gx is equal to dimension of Gx times G. Because G is the regular and invertible map of the group. Yeah?
You have written very strange combination of symbols.
This one.
Yeah.
You should move the closing parentheses.
For example.
I mean like this. And what is difference? Ah, you mean you apply parentheses to dimension. I mean, well, then I should have to write like this.
But otherwise you have parentheses
Just for nothing. Just for nothing. I mean, okay, but anyway. So this is for any subgroup, of course, yeah, because G is invertible. And you know that always that if you have a map from X into Y, so dimension of the image is less or equal than dimension of X. So this means that, and you can map, so from, you can have a look at Gx that maps to Gx times G. So mapping by G, and you go by inverse, just by applying inverse. Yeah, so you can go in the inverse direction. So you see that, yeah, by the way, I have put, yeah, so I have put G inverse here, so I have put G in the wrong place here. Yeah? So you see that you see the following, that dimension of the fibers doesn't depend on the point, and this is equal to this difference. Yeah, so this shows that. So this. So this shows that dimension of F, so P inverse of Z is equal to dimension of gx and equal to dimension of the stabilizer, and doesn't depend on the point. So it does not depend on the point on Z. So this means that the orbit morphism look like this. Yeah, so you just, as in the case of the finite groups, when you consider the corresponding cosets, yeah, so the fibers over the point gx is just corresponding coset, and they have the same dimension as in the case of when you consider finite groups. We see that they have the same number of elements.
Did you just consider some kind of quotient?
No, I mean it is some kind of quotient. Yes, so it comes automatically because you have the action. Yes, so this also shows that Gx is a closed subgroup, and so this existence of orbit morphism is not for free. I mean, so our next step is to discuss how we can produce orbit morphism for any closed subgroup H. So here we get the conclusion because we had an action of G on some algebraic variety. This gave us that the orbit morphism is also the map from G to algebraic variety. And this says that we have the map from G to the orbit, which has a structure of algebraic variety, and set theoretically, so we have, so set theoretically, we have that this is just the set of cosets modulo stabilizer. Yeah? So, and we have considered such cosets. So, so if this map from G to this variety exists, then we can speak about the dimension of the fibers, and the dimensions of the fibers we can look at. So we can look at the fibers as set theoretical from the set theoretical point of view, and so we have identified them with the subsets. And this shows that you can permute the fibers, yes, so by mapping Gx to G by applying the element of G. So, so the next step is to understand, the next step is to understand that to try to invert this procedure. Yeah? So here we have an orbit, and so that it corresponds to the cosets. So the question is if the set of cosets has algebraic structure. So algebraic structure. On the set of cosets. Yeah, so here, so far we actually have the following situations. So if you start with algebraic variety and has an action, yeah, so automatically the orbit, you have the orbit which has just is quasi just it is locally closed subset, and this it has so you can consider it as a map of from G to the orbit, and the orbit is just the corresponding coset. Yeah, so also we have a similar situation if you have the homomorphism of the groups. Yeah, so you know that the kernel of homomorphism that is homomorphism of the groups and the regular map of the corresponding varieties, algebraic varieties. So then you know that the kernel of phi is a normal subgroup, closed, algebraic, normal subgroup. Yeah? So if it is morphism of algebraic groups. And you can try to invert this situation, so by starting with normal subgroup here and trying to map it to the quotient of G by the normal subgroup. And it's so far it's not evident that this object exists, has a structure of algebraic variety. So far it can happen that it is just the group, but you do not know how to introduce the structure of algebraic variety. And we shall discuss how to do it. So yeah, so what we want to do is to try to mimic this situation. So this is called Chevalier Theorem.
It may be that an algebraic group creates a normal subgroup, but the quotient is not an algebraic.
No, but it is not evident. I mean, you have G, you have closed algebraic subgroup, which is normal. The quotient will be always algebraic group, but we shall be proving it now. It's not evident.
But it is an algebraic.
Yes, yeah. It's not evident, yes, so that it has this kind of structure. And the problem is that we shall start with this more general problem, and it won't be evident even after we prove this one, that this is true.
You mean that any stabilizer factorization is an algebraic group?
What?
Any quotient by a stabilizer
Is algebraic variety. So this gives you the structure of algebraic variety. So Chevalier theorem says that suppose H inside G is so G is algebraic group. It is an algebraic subgroup. Yeah, so let us assume that it is affine, because otherwise
is bigger than H, or G?
G is bigger, yeah. Thanks. I always try to keep the notation that G is bigger. So G is some. So let us assume that it is affine, because if you want to work with more general type of groups, it is so it is more complicated to work with them, and it should be done by different methods. And if you, but these theorems should be available as well to build up theory. So if you are considering this closed subgroup, then there exists inclusion of G mod H in the projective space where G, so you have homomorphism of G into the, so where G acts on this vector space V. Yeah, so where G acts on the space V by linear transformations, and this inclusion is done as follows. So you have the vector V that represents a line in projective, a point in projective space, and H stabilizes V. So this is just an image of the orbit morphism. Yes, so G mod H is isomorphic to G mod H. That gives you the set of cosets, a structure of algebraic variety. Yeah?
For any G and H, we can find
Yes.
V such
Yeah. There exists V, and the embedding of algebraic variety. This is a slight problem because this, I mean, if you want to apply this, so this gives you the structure of algebraic variety on G mod H, and this tells you that this supplies G mod N, the structure of algebraic variety, but there is one step that should be done here as well, that if it is a different theorem, just that if H n is a normal subgroup, so algebraic group, and this is normal subgroup, closed, well, normal algebraic subgroup, then G mod H is a linear group. Yeah? Or affine group. Yeah? So just affine variety. That gives, so that puts G mod H as a subgroup in some GL. This realizes this group as some subgroup in some GL N for some, well, GL W. So the problem is of applying this theorem directly, that in general, in order to speak about cosets, even starting with affine group G and affine group H, you cannot stick to algebraic. So you cannot stick to algebraic. So you cannot use only affine varieties, affine algebraic varieties. You should use quasi-projective varieties. So this is embedded as an orbit in projective space. Okay. So.
What do you mean by embedded as an object?
I mean that there is I was writing this here. Yeah. So I mean that on V there is exists an action. Yeah. So G acts on V by linear transformations. So that means that you have homomorphism to the and if you are acting by linear transformations, then G acts on this projective space. Yeah? So this I claim that when G acts on this projective space, there is a V such that H is stabilizer of this line, and this allows you to just take the orbit map that is an orbit of this vector V, and just identified it with the set of cosets.
So H is a co-stabilizer of V, not just.
H is a stabilizer of the line, of one line. So for this particular vector, yeah, so that means, so remark, yeah, so H, so what does it mean that H preserves V? This means that H multiplies, so each element of H, when it acts on V, so it multiplies V by some number that depends on H. Yeah? Okay? So this is just some number, and this number is non-zero. So x of H belongs to the multiplicative group of the field. And moreover, it is, so it is, H is acting by the linear transformations. So H is acting as a subset in GLV. So on V, it should act by the linear, one-dimensional linear transformations. So that means, yes, by the scalar matrix. So this is just a character. Yes, so that if you take the composition of on V, yes, so this is just bilinearly. So it is just a chi of H2 applied to V. And then the subsequent application of H will give you, so it is H1 applied to this one. You use linearity. So formally, you use linearity of your map, and this allows you to write down that this is chi of H1 times chi of H2 of just a multiplication by the scalar. So this means that, so since this vector is preserved and you are acting by one-dimensional linear transformation, this gives you the character from H into K star. Yeah, so character is homomorphism of algebraic groups. So homomorphism of algebraic groups.
Is it so that when you multiply such PF means that the theory holds?
Yes, it is not unique. I mean, there could be quite many embeddings.
They will be isomorphic as varieties, even if they are.
I mean, so the G mod H will be isomorphic. The orbits will be isomorphic as the varieties. P of V won't be isomorphic. I mean, they could be different, of different dimension. Yeah.
You assume that G is affine, but it works for any projective.
So yeah, I assume that I assume here that G is affine, but yes, so for not affine varieties, it is a little bit more subtle because you should consider the theory of Jacobian or Albanese map. So this is reduced. So this kind of theorems are reduced to the affine case, and I mean of G, and in general you should be able to work with abelian varieties, and this is just in order to work with them, you should be able have a universal map to abelian varieties, which is called Albanese map. So it is completely out of the reach of this course.
And if GSSA, the same method works?
Yeah, you shall see how it works in a second. Okay. I mean, if it is related, so it uses the algebra of regular function actually. So it is. Yeah, so why the problem here with being affine? I mean, in the setting, because we shall use that G is characterized by its algebra of regular functions, and also the subvarieties are also characterized by the algebra of regular functions. А мы во сколько заканчиваем?
Вообще говорим 14:20.
Хорошо, тогда ускорюсь. Yeah, ага.
Yes.
No, okay, yeah.
Later you have
It depends if you, so if you just is able to attend it. Yeah, so let us start as follows. So there was, we look at H inside G. Yeah, so we looked at how we can characterize H as a closed subset. So we can think of ideal of functions that vanish on H. Yes, so just ideal of functions on ideal of functions that vanish on H. And notice also how you can characterize your element. So this, so you have this collection of functions. So this ideal is finitely generated.
Is this functions? Could you remind what are K of G?
K of G is just I mean G is embedded in some affine space. And so here you have polynomial algebra. It is just given by the collection of equations. You just restrict polynomial functions to G.
So H is embedded accordingly, and we think.
Yeah, so H, so you have to specify the equations here. So G1, G1, GK. And then you have to specify equations for H. Yeah, so F.
H defined by the embedding of. I mean, is closedness in H.
I mean, we use that H is closed, meaning that it is defined by ideal, defined by the collection of equations. Вже, да. Ну, вы можете просто думать об этих уравнениях как о пришедших из ограничения в А. Поэтому, чтобы получить, что H замкнуто вот в этом А, вы можете взять вот эти уравнения, определяющие G, и поднять вот эти как угодно. Эти поднимаются как угодно, вы выберете любых представителей. Но разница поднятий будет отличаться на вот эти вот уравнения. So you get a finite number of generators. So finite number of generators. And you can try to check that G belongs to G if and only if G belongs to H, if and only if Gx belongs to H for any x that is from H. Yeah? So this is evident. Yeah? So to check that G belongs to H, you have to take point from H and you apply G, and it should be in the same thing. And so to check, so this means that in terms of this collection of equations, this means that we have to check that xg, fi xg vanish for any I. And this means that so this means that we should have the following. So if fi vanish on x, so this is condition that x belongs to H. Then you have you can rewrite this condition simply as saying that fi of fi vanish on x. So this means that x is a point of x. Then fi xg also vanish on x. Fi also vanish on gx. So this can be rewritten as that the gx, I can write down g inverse, it doesn't matter here. So this means that the action of g on these functions just keeps this function in the ideal. Yeah? Okay. So this is condition of that so that G belongs to H if and only if rho of G applied to Fi belongs to this ideal. Rho of G is just the following. Rho of G is just the following representation of G to the set of regular functions that maps an element G. So it maps K of G. So rho of G maps K of G, the set of functions to the set of functions, by saying that f of x maps to f of g inverse of x. This is an action. So I am just rewriting down this in these terms. But notice that you want to have the following. Yeah, so you want to have the following, that just so each fi for any I, we proved that the linear span, so so which is just the corresponding applying elements gi, so for any f, yeah, for any functions, we can apply the element gi and take the linear combinations. And this is a finitely generated module. So if you take this collection of functions, they all live in some finitely generated module where V is just formed by the sums of these invariant modules. Yeah, so you can take in K of X, you can take in K of G, you can take all this. So each Fi sits in some finite dimensional G module. You can just take the sum of this finite sum of this collection of modules. Yeah? So this is finite dimensional vector space. Finite dimensional vector space. Invariant under G. Under G. In K of G. And this means that this characterization of belonging to H can be rewritten. Yeah? So this means that if you take, so we know, so here we know that Fi belongs to V, and V sits, and this means that in order to check, so you know that at least a row of G of I sits in V a priori. So if you act by G, we're still in V. So this intersection, checking this is equivalent. So this means that G belongs to H if and only if. So you know that Fi belongs to V intersection, and Fi belongs to V, and at the same time to ideal EH. Yeah. So this means that you can put this EH, and you can denote this as a subset W. So this means that G belongs to H if and only if Fi, for any Fi that belongs to W, this, so for any F that belongs to W, I write down F row of G. F sits in W.
I have a question.
Yeah.
So if you have a polynomial F, then this polynomial generates a finite generated module.
Да.
This separation.
Да.
So this operation is following. Take
Oh.
F and take all the images of F under row. Yeah?
Ну да, то есть мы берем F, к нему применяем различные жииты, ну просто элементы группы, берем их линейная комбинация. Но вообще говоря, этих элементов...
Это элемент группы.
Да.
Не многочлены, которые вот там над А.
Да. Ну вот давайте ро жииты напишу. Ну эти многочлены, это вы меня уговорили написать. Ну у меня буквы там закончились. Вот. А это, ну, ро жииты. So this is row of Gi applied to F. Yeah?
And can these different modules generated by different F intersect?
Ну, конечно, мы просто их берем сумму. Ну, не прямую, а сумму, в смысле, ну, порождаем ими векторное пространство. Сумма как подпространство.
Получилось все, что все КЖ получилось.
Ну как, у нас конечное, у нас этих конечно. So we cannot get whole kg because kg is not finitely. I mean, if g is fine, is not. I mean, it can happen that that v is equal to k of g only in the case then k of g is finite, because it is equivalent in. So saying that k of g is finite dimensional over k as the vector space is equivalent to say that g is finite.
So I didn't understand what you were talking about after when you know if I like this.
Yeah, we know that from the beginning that we have taken FIs, this collection of generators. First of all, we know that they are from IH, and in the same time, they are from V, G-invariant vector subspace. Yeah, so I can put like this. Yeah? So also, automatically, rho of G of Fi sits inside V. And if I claim, if I want to rewrite this condition, I'm saying that I'm taking Fi from IH. So I want to take this intersection. So Fi so instead of Fi, I can take a larger collection of polynomials. I mean, to check a larger collection from the ideal Hi. Yeah? So to check that G is inside H, I can take more polynomials Fi to check. Yeah, so this should hold for any I, yeah, for in this collection. Okay. So I'm saying that these conditions. So I just say that I should say take both conditions, Hi and that Fi's were the elements from V. Yeah, so that we have constructed here. So I can take Fi from Hi intersection of V and reformulate this condition of saying that G belongs to H if and only if rho of G Fi sits inside H, but I know that when automatically this will sit in H intersection with V. So I can rewrite the condition as follows. So G belongs to H if and only if for any function from W, I put W to be this intersection, rho of G is still in W. So now we can almost finish the proof. So we have restated our theorem as follows. So we had a vector space V, and rho of and the G was acting. G acts on V by linear transformation. So this means that G maps to GLV. So then you have a subspace set. W is a subspace. And we have the following condition. G belongs to H if and only if GW belongs to W for any W inside W. Yeah? So element G belongs to H if and only if it maps the linear subspace into itself. Okay? So in order to, but it is not what we wanted. We wanted to say that we wanted to find the map from G to some subset of linear transformation. So this means that H is a stabilizer of this W, yes, so of the subset. But where? Actually in the Grossmanian. Yeah, so this means that if you consider the Grossmanian of dim W linear subspaces in dim V dimensional space, H, so this saying this thing is saying that, so GW sits inside W. So saying that G belongs to H if and only if H fixes W as an element of Grossmanian. But so here I do not actually need the Grossmanian itself. I shall need only a Plucker embedding. So G fixes this linear subspace. And actually, if, so one can notice that if G acts on the vector space V, it acts on the linear, it maps the linear space of the fixed dimension to the linear space of the fixed dimension. That means that G actually acts on this Grossmanian, yeah? This Grossmanian. H fixes W. The element fixes W, yeah. So H is the stabilizer of W in the group G. Yeah. So but for me, I need only Plucker embedding so far. So I want to rewrite it in terms of that H fixes one-dimensional line. And in order to do it, I just take the highest wedge power. Yeah, so just take L to be a dimension of W, well, S to be a dimension of W. And you can, so the inclusion of W inside V induces the taking, so you can apply operation of wedge product. And so this embeds this subspace here. But notice that this is just a one-dimensional subspace because I have taken the highest exterior power. So if you have W1, Ws is a basis of S of W, then this is just generated by one element, one basic vector, which is written like this. Yeah? So this tells you that just notice that G acts on V. So of course it acts on standard monomial. So just by the standard way. So a standard monomial maps to the corresponding standard monomial, and you can extend the section by linearity. So extend by linearity.
I see that the proof may be done, may provide a way to calculate the action on such V and find this V. Is it?
Yes. Yeah.
So it's a constructive proof.
I mean, yes. If you have the computer algebra system, I mean, it's not very easy, but it is constructive. Yeah. I mean, if it is a computer algebra system, you just realize that this algebra is a quotient of polynomials. You should have Grobner basis to calculate this ideal. So you just have to take these polynomials to be just a basis of this ideal, then the only thing that you should have, you should know how the group acts on its generators on G, so to provide this linear subspaces V and W, but this is purely constructive here. So you notice that G acts on lambda S of V, so this means that we embed G. So we map G to this linear transformations of lambda S of V. And this means that H is a stabilizer of this line. So this means that the problem is that this line is defined up to the scalar. So W1, Ws, so it is defined up to the scalar. The vector, yeah? So this means that saying that H fixes, so G fixes W, is saying that if I apply rho of G to W, yeah, so it is just some scalar, so the character of G that times W1 Ws. So you see that you cannot embed, so in order to say that H is a stabilizer, you should take the projectivization. Yeah? So this means that now this vector, so the line formed by this vector sits in the corresponding projectivization of this wedge power of V. And the H is a stabilizer of the line. H is a stabilizer in G of this vector under Plucker embedding. Yeah? So this is called, of course, Plucker embedding. And we just realized our group as the stabilizer in the Grossmanian, but Grossmanian is embedded in this projective space of rather high dimension. Yeah? So this realized H, and the homogeneous space is just the orbit of this vector, of this line.
So do you mean that the action was induced by a Grossmanian?
I mean the following, the Grossmanian sits. I mean the embedding that I have written. Yeah, so here in as the W to the wedge product, you can start with any subspace, not specific one, just with the subspace of dimension S. Yeah. So if W tilde of dimension S, so you embed the wedge product of W tilde into wedge product of of V, and this gives you embed. So our vector here, so our orbit G of this vector W1 Ws. It sits in the Grossmanian. Yes, I mean, so just to write it down in a good manner. So as dimensional Grossmanian in V-dimensional space embeds in the projective space of lambda S of V. And here you have, here you have the element W1, Ws. And our subspace W maps to this element W. Yeah? So the class of this subspace maps into this W. And the orbit sits inside this Grossmanian. Yeah? So this, the orbit of this vector sits here and here. But you can look at this orbit here. And this maps to this orbit G of W1, Ws. I mean, the Grossmanian is embedded here, and G acts on this space, and acts on the G maps W tilde to W tilde. It maps to the class G of W tilde. So this gives you the action. So you have the action of V, and it induces the action on Grossmanian and the action of the corresponding projective space.
What is the classic equivalence of W? What is also...
Ну, это как элемент в Гроссманиане, да? Ну, в смысле, ну, как бы говоря о векторном... Нет, ну говоря о пространстве об элементе в Гроссманиане, ему соответствует векторное подпространство. Поэтому...
Все вектора, которые лежат в нем,
да.
в одном классе эквивалент.
Не в одном. Нет. Ну, в смысле, это не класс эквивалентности W, это обозначение, что W вы сопоставляете точку в Гроссманиане. Ну, таким вектором. Ну, вы же не вектору, который лежит. Да. Ну, что это точка в подпространстве, да. Ну, а это как бы как действие на классах. То есть, ну, действие на точках в Гроссманиане. Ну, то есть вы к W можете применять элемент G, но действуя на точках в Гроссманиане, вы класс должны, в смысле, точку перевести в точку, да.
Гроссманиан — это какое-то гладкое подмногообразие, получается?
Ну, вот оно реализовалось в качестве... Ну, я не показывал, что оно гладкое, но отображение Плюкера, ну, которое вот отображает... Ну, вы берете ваше подпространство, выбираете произвольный там базис и берете S-тую внешнюю степень. И тем самым вы можете отобразить ваше S-мерное подпространство в внешнюю степень, выбирая базис, то с точностью до скаляра. Любой другой выбор базиса меняет ваше вот это внешнее произведение просто на скаляр.
То есть это вложение, алгебраическое вложение в проективное многообразие.
Проективное пространство, да. So, как бы тут проблема в том, что я не показывал, что оно алгебраическое. Но вот это вложение, вот отсюда сюда, да, я не в смысле, что вам вообще на этот Гроссманиан, в принципе, наплевать, с точки зрения доказательства. Потому что у вас здесь есть действие вот это на векторе, на элементах здесь, и вы просто берете, есть какое-то действие, берете какой-то вектор и берете его орбиту. Все, тут ничего не нужно. А вот, если говорить о Гроссманиане, то я тут я любому подпространству в V S-мерному я таким образом могу сопоставлять элемент внешней степени с точностью до умножения на скаляр, потому что я беру весь базис, когда вы применяете линейное преобразование, то он меняется на определитель, да? Это одномерное пространство, больше векторов тут набрать нельзя. Но я здесь ничего не говорю о том, что я вот это дело задал уравнениями вот здесь, да? Что я не написал уравнение на тензор здесь. Но вообще говоря, вот что такое элемент здесь? Это набор линейных комбинаций вот таких векторов. И я не написал условия, которое говорит о том, что вот этот тензор представляется вот в виде внешних степеней для какого-то базиса. Это называется соотношение Плюкера. И я их не писал, чтобы показать, что вот это алгебраическое многообразие здесь. Ну вот. Но для того, чтобы это сделать, это надо как бы, ну это надо написать эти уравнения так или иначе из каких-то, ну, соображений. То есть вот как бы. Но вот это уж вы мне поверьте, это мы давайте оставим курс алгебраической геометрии. Ну вот, что вот это можно здесь написать уравнениями. Okay, so maybe it is a good point to stop now, and I can answer your questions. So next time we shall